All right. Hello, Bree and Tony. I dropped this earlier. I wonder if it still works.
Just spit some bottoms.
What'd you say?
Just rap on it.
You got it like the McDonald's.
Oh, that's better.
It's like super shiny.
I thought maybe it was, it's like, oh no, I broke it. But you don't know what we're laughing about. You cannot. All you can see is the board. Bree. I should talk like Bree the entire hour.
I feel like I feel weird if I was watching this video.
Thank you.
It wasn't that for me.
Hey, things went really well. And you could kind of estimate, you kind of knew beforehand what was going to happen.
Let's go
Awesome.
live, dude.
All right. And you don't need a pass. You're all set. Awesome.
The first
Thanks for
15
coming in.
Just talking.
All right. That's how you make up a lab. Okay. Let's give this a try. Watch this. Oh, no.
Very impressive.
Yep. First thing I do is screw up. That was my fault. There we go. Okay, now, watch this. I click on that so I can draw pictures. Then I click on this, and it'll just give me a blank page. Okay, so, helps if I have a book. We're looking at number 11 first, correct? And I got to move the TARDIS over to chapter 5. Okay, number 11. I remember this happening. This is July 17, 1981. This was a big deal. It was the Hyatt Regency. It was packed with people, and people were on this balcony, and they were dancing, and the balcony collapsed. And a lot of people were hurt, injured, killed, and it was a huge thing.
Wait,
What? Oh, that's the question.
Yeah.
See, I just did what a lot of students do.
Yeah,
Okay.
I did this too.
The Hyatt Regency Hotel, though, that was a big deal back in 1981. Were you alive in 1981?
No,
I didn't think so.
I didn't know that happened.
Dang it. I started teaching in 1988. Were you alive in 1988?
No.
See, I can't do simple math this morning. So
10 more years.
Yeah.
What?
10 more years after you started teaching.
So 1998 you were born?
Yeah.
Yeah.
I didn't know.
97.
Yours was
90.
You're getting there.
2002.
Isn't the freshman 2000?
Yeah.
Or is it no next year?
No, they're like 2001, I think.
Oh, really?
Okay, Bree and Tony, you can skip like the first 5 minutes of this video, obviously. Okay, let's do it. A .340 kilogram particle moves in the xy plane according to those two equations, one for the x, one for the y. And it says, okay, we got all our units. At t equals 0.7 seconds, what's the magnitude and angle relative to the positive direction of the x-axis of the net force on the particle? And what is the angle of the particle's direction of travel? Ooh. So the question was 11C, right? I don't have to do A and B. Speak now or forever hold your peace. Yes, ma'am?
Could you do A, B, B?
Absolutely. Let's do the whole thing then. Alrighty. So that means I got to write down all this stuff, and my glasses are nearby. Here we go. Okay. So mass. Okay. Oh, look. Let's try that again. I do not know what that symbol is, but
You just created a new symbol?
no, I think this board was briefly possessed by some demonic agent. That is probably something we should erase before bad things happen. There. Whoa!
Don't touch it. Don't touch it. Just let it live there.
Okay, school is canceled for today until we can get an exorcist in here.
It's the demon board.
Holy mollies. I'm really worried now. Okay, let's ignore it and pretend that Beelzebub is not among us. 0.340. I'm obviously going to take next hour and share that with
That's so awesome.
No, you gotta show.
Share the.
You have to.
Holy moly's! What the heck?
Yeah, I would just go watch
It's
those.
like a square.
Yeah, this will be on YouTube as like evidence for. Oh goodness.
Kind of like a heartbeat monitor with like a Z.
Yeah.
Oh, I tried for an M there. That was an M up there. But yes, the powers of darkness took over. All right. So -15. Bree's going to be, playing this for her dad or something. And like, what are they doing in school nowadays? Oh gosh. All right. I'm dropping some of the sig figs, as you notice, and we can put them back when we're done, but they just get kind of clunky. -9t squared. All right, so this gets kind of complicated, doesn't it? Make sure I wrote everything down correctly. And then t equals 0.7 seconds is the special time. I'm going to run out of room here. Okay. And the first question is magnitude direction of the force, the net force on the particle. So if you're after net force, F equals ma is your friend, right? So you need the mass, you need the acceleration. Hey, look, we got the mass, we've got the position on either axis. So let's see, I'm going to have to conserve my room a little bit. I'm going to claim that v of t in the x direction is going to be 2 minus 12t squared. And if I mess up, please yell at me. And that v in the y direction is going to be 7 minus 18t. Okay, then acceleration in the x direction. It's a function of time. I don't always write that t in the parentheses there. Is going to be negative 24t. Acceleration in the y direction, negative 18. Looks like a constant acceleration into y. I'm leaving off the units. Okay? So that means acceleration is going to be negative 24t I hat minus 18j hat meters per second squared. There, I'll put the units on. There we go. Okie dokie. So if you want to know the net force, we're going to stick 0.7 seconds in for t, multiply by the mass. Oh my gosh, look at this. 0.340 kilograms times, Lena, do we want to punch that out or we want to do it like right now? We could say negative 24. That looks terrible. Okay, let's try this again. See, that wasn't the mark of Satan, so it did come back. Okay, so I'll say negative 24 times 0.7, whatever the heck that is. And that's I hat. I still got to keep them I hat, j hat. Okay. So if I punch this through, the 0.340 times this, whatever that is, and the 0.340 times 18, I will have, in unit vector notation, the net force. If they want the magnitude and direction, we know how to do that. So just for kicks and giggles, let's punch this through and see if I get it right. That's the entertaining part. See if the teacher can do the problem. Negative 24 times 0.7 times 0.34 gives us negative 5.712. Okay. Negative 18 times 0.34, whoa, there we go, is negative 6.12. Okay, so technically we've got our answer. It's probably not in the form we want, but that is the answer, assuming I didn't make any silly mistakes. Now they want the magnitude and the angle, so we know how to do that. I always draw a diagram. I mean it's pretty obvious what we need to do, but I need a visual. That's just me. So it may be a crutch, but what the heck. Okay, and then I leave off the negative signs because it's pretty clear that the directions are negative here, and the negative signs are just going to gum up my calculator. So if I find that magnitude there by Pythagorean theorem, there's our sigma f, magnitude equals the square root of 5.712, whoops, that's a 1, 2 squared plus 6.12 squared. Okay, an angle, I'll randomly choose that one. It's so many degrees south of west. So the number of degrees south of west is going to be inverse tangent of, in degree mode, opposite 6.12 over 5.712. Dun, dun, dun. We should, if our calculators are working, have the magnitude and direction. Okay. Man, just filled up that magic whiteboard. So, are we getting anything close to what we should be getting? Or do I have to track down an error somewhere? Square root of 70 is 8.37. Does that ring a bell? Was that up there on the board earlier? Oh, thank goodness. All right. So inverse tan of 6.12 over 5.712. Okay, getting like 46, 47 degrees. We'll call it 47. If 3 sig figs? That's right. It was they piled sig figs in. They had like 3 and 4. So let's go with 3 sig figs. We'll say 47.0 degrees south of west. Okay, part C, which some of you asked for. What is the angle of, okay, this is like out of left field. They're asking you something totally different. The angle of the particle's direction of travel. Okay, so when they ask you, what direction is something traveling, are you going to look at its position, velocity, acceleration, or net force? Velocity. So they're trying to trick you, right? This whole thing has been about acceleration and force, and then they say, what's the direction of travel? They're just poking you a little just to get you to remember that we need to go here to find the direction of travel. So we're going to stick 0.7 into each of those, get the velocity in unit vector notation, do an inverse tangent dance, and come up with the direction of travel. So I'm going to need to clear some of this out. So hopefully this is making sense. I don't want to clear everything out, but here's the big eraser. Let's see what happens. I'm just curious now. Oh! Satan has left the building. Goodness sakes. That was one of the weirdest things I've seen this board do. And I've seen it do some pretty weird crap. All right. So, velocity at that time, 2 minus 12.7 seconds squared, I hat. Oh my gosh. Plus 7 minus 18 times 0.7 seconds. It was 0.7 seconds, right?
Yep.
Okay, good. If I put in the wrong number, my face will be red. And so we come up with those two components, and then you kind of know what to do. But for the kids at home, let's figure this out. 2 minus 12 times 0.7 squared turns out to be like negative 3.88. It's amazing what you can do with unit vector notation that is really hard to do in other systems. So this is all I teach, is unit vector notation. If you read the physics book that comes with honors physics, they do it totally differently, but it's not as powerful. Negative 5.6. I should stop talking while I'm calculating because I'll mess up. All right. So if they asked, there's the velocity at that time, but all we want is the direction of travel. So we're going to say, okay, negative 3.88, so I'll just write a 3.88. We've got a negative 5.60. Okay, choose one of those angles randomly. inverse tan. The direction of the velocity is going to be inverse tangent of 5.6 on top and 3.88 on the bottom. And let's say a little prayer. And 5.6 over 3.88. And I'm getting like 55 degrees south of west, 55.3.
That's what I got, but the answer key said it was like something different.
Okay, let's interpret the answer key. The answer key might not be wrong.
Interesting issue, yeah.
What did they say in the answer key?
It's asking it from like the positive x.
Oh, so in the answer key they're going, watch this. They're going, yeah.
No,
They're going the other way.
Oh, you're joking. All right. Wow, why would they do that? So they're giving you negative direction from the positive x-axis. Yeah. So when you find an angle, don't just assume you got it wrong, because there's like 50 ways of telling somebody that angle. Really, there's some that we don't cover and you don't even want to know. So yeah, if you ever look in the back of the book and your angle's wrong, don't jump to conclusions. Just check to see what they're doing. Grad students write the key, and they do some weird stuff sometimes. All right, so that was a long one, but hopefully I answered your questions. Number 13, the salami problem.
Why did they use salami for this? They could have used anything, like just like a block of mass, but they chose salami.
Do you have something against salami? The salami
Wow.
power kill your parents.
So the real Andrew Gardner finally shows up, right? He's starting to whine about the problems. You just have a thing against meat, right?
I don't know, I thought that was strange.
Oh, okay. They do some stranger stuff. I mean, it's like the armadillo, right?
True.
Yeah. And then later on, there's penguins, All right, 11 kilogram salami is supported by a cord that runs to a spring scale, which is supported by a cord hung from the ceiling. What is the reading on the scale, which is marked in weight units? Okay. So you've got 11 kilogram salami there. What's its weight? Yeah, 11 times 9.8, right? So let's clear this baby out here. Whammo. And so 13, weight, mg. So the first one, not too terrible. Okay. Whatever that is. I think you just told me. 107.8? Really? Okay, 3 sig figs. Let's call it 108. Woo! Next. Okay, in the figure, the salami is supported by a cord that runs around a pulley. Attach it to the wall. What's the reading on the scale? Do you remember me doing this demo last year? It was a long time ago. I had 2 masses. I didn't have any salami.
And you had 2 people go up in that pool.
Oh, I did that too. Okay. So, looking at that diagram there, what do you think the spring scale reads? What's the pulley doing? Is it changing the amount of force, or is it changing the direction of the force? There's only one pulley. Now, if you've got a block and tackle, you can change the amount of force needed to lift something, but that's just a single pulley. So the tension in the rope and the tension over where the pulley is at is really going to be the same. And I was going to set this up today, but I couldn't find my pulleys. I was searching and searching all morning, and it turned out that the box containing my pulleys had fallen back behind where all the other boxes were. So, it was my fault. But, So, we've got a spring scale and a pulley and the same salami down here. I don't know. Would you agree it's going to be the same reading? Heathy, are you okay?
Yeah.
Sarah? Kind of? All right. Because some of you are looking at me like I'm nuts. Which, debate. Okay. Now we take the wall away, we put another pulley here, and we drop a salami. And the question is, what's going on? Now, back in the moment when this was a wall and not another salami, with how much force was this string pulling on the wall? Okay, so let's back up. Let's make this a wall again. The wall is feeling a force, right? This string is pulling on the wall. With how much force do you think? Yeah. So the wall feels a force of 108 newtons. What's the wall doing according to the third law? It's pulling on the string with 108 newtons. That's the third law. You pull on a wall, it pulls back. I push on Heath, he pushes back. He doesn't have a choice. He doesn't even think about it. Okay? It doesn't matter if I push him on the hand or push him on the back or something, try to push him over. I'm receiving a force back on my hand equal to the force I'm applying to him. So if this string applies a force to the wall of 108 newtons, the wall pulls back with 108 newtons, period. This force is on the wall, this force is on the string, so be careful. This is not a free body diagram that I'm drawing up here. Okay, so be careful with the idea. Now, let's get rid of the wall. Yeah. And do the pulley thing. Okay. What's this salami doing? It's providing a force of what? In that direct, wasn't that what the wall was just doing? Yeah, it's exactly the same situation. Yeah, it doesn't matter if we tie it to the wall or we hang another salami. The point of this problem is the third law. That wall applies a force on the string the same as what the salami is doing there. It's exactly the same situation if you believe the third law works. Remember I said the third law is like the one that everyone gets wrong. Did we get to the third law the other day? Okay, we'll get to that today. We did get to it last year, so it's fair game. Sorry. But we'll be there. We'll be there in just a minute. Okay. Number 15 shows an arrangement in which 4 discs are suspended by cords. Okay, check this out. This is a mean little problem. You had questions on this one, right?
Yeah.
Okay. Don't let me do it if, everybody's got it and you just kind of sit there and say, oh, we'll just watch Mr. Evely flail around for a while. All right, so these things are hung by discs. These discs are hung by cords. And let's see, what else do we know? Then there's a frictionless pulley, blah, 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 blah. And the top cord is pulling with a force of 98 newtons. I'm just going to write 98 newtons. I'm not going to put an arrow there yet. Which is attached. The tensions in the shorter cords are as follows. Oh, okay. It's kind of irritating they use T for force because they mean for it to be a tension. They do the same thing on the AP test, which bothers me to no end. T2, 49. T3, 9.8. Okay. What are the masses of the discs? Disc A, disc B, disc C, and disc D. So just find all the masses. So we don't care what order we find them. We're just going to find them. And they're labeled from the top, A, B, C, D. Okie dokie. All right, tell you what. We don't care what order we do this. Take that disc. Isolate it. Just think of that disc alone. Okay? Let the others fade out of focus. There's 2 forces on this disc. We've got the string pulling up. We've got its weight pulling down. How much is the weight pulling up? How much is the tension pulling up?
9.8.
Yeah, 9.8 newtons. So that's T3. This is the weight of disk D. I'll call it just FD instead of FWD. It gets kind of crazy. So if this disk, oh, let me ask you this question. Is this disk accelerating? Nope. So the up force is 9.8. What's the down force? 9.8. So it has a weight of 9.8 newtons. Therefore, it has a mass of 1 kilogram. Woohoo! Next. This tension, T2, it's a force being applied here. It's also pulling down on B, but I'm going to leave that alone for just a second. I'm going to switch colors. There we go. T2 also pulls down on B, but I'm not worried about that at the moment. Okay. What's T2 doing then? This upward arrow, this little blue arrow, what's that doing? What's it holding up? Oh, so both C and D both C and D are being held up by that 49 Newton force. Oh, are they accelerating? No. That means the whole thing in blue has a downward force on it. This is the weight of CD of 49 newtons. Can I find the mass of CD then? Sure thing. Mass equals weight over 9.8. It even rhymes. So what's 49 divided by 9.8? 5 kilograms. Beautiful. So what's the mass of C? 4 kilograms. All right, so he's a 1 kilogram mass. He's a 4 kilogram mass for a total of 5 kilograms. Keep going. Okay? That's one way to do it. Another way to do it would be to just isolate C and say, okay, here's disk C. I've got an upward force of 49 newtons. I have a downward force of its weight and a downward force of 9.8 newtons. Does that make sense? The string below C is pulling down at 9.8 newtons. That's what it says here. The string above C is pulling up at 49 newtons. Plus, C's got weight. So another way of doing this is to say, okay, the weight of C is going to be 49 minus 9.8, divide by 9.8 to get the mass, and you'll get 4 kilograms. So do you see the other way of doing it? You don't have to do it that way, but I need for it to make sense to you. So we could just isolate C alone and put all 3 forces on it. The thing about tension, tension's hard. If they tell you the tension in this little piece of string is 58.8 newtons, that means it's pulling up on B with 58.8, and it's pulling down on A with 58.8. We're saying the tension in each little segment of that string is 58.8 newtons. Think of it like tug of war. You know, if we take Ethan and me and we put a rope between us, we start pulling, that rope's going to pull on me with a force of, 1,000 pounds, because we're amazing. And it's going to pull on him with an equal amount of force. We have no choice because the tension is distributed throughout the entire rope. Okay, that's a lot of words. I hope that made sense. Tension is kind of weird. All right. Any questions? How you doing? What? We're not allowed to have just 2 minutes left. I do not like assembly days for this reason. Who? All right, your job for the weekend is to read chapter 5 and do the problem, the challenge problem. And I would like you to direct your reading a little bit. Please try to answer questions 1, 2, 3, 5, 6, 10. I haven't given questions yet.
1, 2, 3, 5, 6, 7.
Yeah. 1, 2, 3, 5, 6, 10. So as you're reading, this is chapter 5. The questions will help you to pull some things out of the reading, hopefully that makes sense to you. Alrighty. I hope this was helpful to the kids at home.